Hello everyone, and welcome to Lab Manager's Ask the Expert webinar series. These webinars bring together leading laboratory professionals to discuss important industry topics. My name is Betsy Young, and I'll be moderating today's webinar entitled Successful Life Science Lab Redesign for Lab Managers and Safety Officers. We like our webinars to be very interactive, so we encourage you to send us your questions at any point during the presentation. Many of you know the drill, but for those of you just joining us, just type your question into the question box located at the bottom left-hand side of your screen. We'll try to address as many of these questions as possible during the Q&A session. If we happen to run out of time, I will forward any unanswered questions to the presenters, and they can respond to you via email. Additional resources can be accessed through the resource window located on the left-hand side of your screen, and you may also move or resize any of the windows simply by grabbing them at the top or stretching them at the bottom right-hand corner. At this time, you may need to move or minimize some of the open windows to see the live view. This webinar recording will be available early next week on Lab Manager's website. At the end of this webinar, we'll share that link with you, as well as the contact information for our speakers. At this time, I'd like to introduce our speakers who join us today on behalf of Labconco Corporation. Matt Anderson is currently the Biosafety Officer at University of Nebraska-Lincoln, where he's been since 2009. Prior to that, he completed a one-year postdoc in biosafety at Washington University in St. Louis. He holds bachelor's degrees in biology and chemistry from Dana College in Blair, Nebraska, and a doctorate in chemical biology from Washington University in St. Louis. He's a registered biosafety professional through ABSA International, and he's active in ABSA International and Midwest Area Biosafety Network, currently serving as the co-chair of the ABSA E-Communications Committee and as president-elect of Mabion. Also joining us today is Brian Garrett. Brian is the product manager for biosafety cabinets and ductless fume hoods at Labconco Corporation. Since 2010, he's been accredited as a lead green associate with the U.S. Green Building Council. Before joining Labconco, Brian was a laboratory director for the Institute for Environmental Health Laboratories in Omaha, Nebraska, where he focused on planning and management of 2 labs in the beef industry, analyzing foodborne pathogens. He's a member of the Controlled Environment Testing Association and American Biological Safety Association International, and sits on the Joint Committee for NSF-ANSI Standard 49. Thank you both for joining us today.
Hello. Today I'm going to share my experience as a safety officer with lab renovations, lab redesigns, and new lab builds. So what makes a lab safe? In my experience, there's 5 key areas that I feel contribute to a safe lab: design, engineering controls, procedures, the personal protective equipment or PPE, and the people. I'll discuss each of these areas during my portion of the webinar today. But first, I wanted to talk about how to make labs safe through controls. This is the hierarchy of control that should be used to eliminate or minimize hazards in the workplace. These are also good things to consider when designing new or renovating existing labs. Evaluate if an existing space needs to be maintained or if it can be eliminated. If you are in an older space, don't be content with replicating your existing lab with new materials. Now is the chance to rethink, to improve, and to design for the future. Is there a better way to do things, better equipment, better processes? Now is your chance to make changes for the better. I know a lot of scientists like to argue, I've done it this way for years, why do I need to change? But the answers are times are changing, people want to be safe in the workplace, and the public is starting to demand safe labs so they feel safe outside the labs and reassured that nothing in the lab is going to get out and harm them. So as you look at this hierarchy of controls, you start with eliminating the hazard, and if you can't eliminate it, you see if you can replace it and substitute for something else. Then you look at engineering controls, and administrative controls, so changing the way that people work, and then finally is instituting that PP component. And this, like I said, the same thing can be done for looking at your redesign. First of all, you need to evaluate whether you can, you need to replicate that existing design in your new facility, or if it can be eliminated, and if there's a better substitution for a process that you're using. And then you also want to look at your engineering controls, what can be improved. A lot of older buildings don't have enough engineering controls or capacity in their ventilation and cooling systems to accommodate newer procedures and containment devices. So those are some of the things you need to consider. So when you're looking at lab design, you want the design to be adaptable to changes in research over time. You want to try not to design the space for a specific type of research that would be expensive to redesign for a future occupant. So you want to make sure that the design is flexible into the future. The infrastructure should be able to handle future needs, and some of the things you consider as far as future needs are going to be your engineering controls. That's examples of containment devices, fume hoods, biosafety cabinets, glove boxes, anaerobic chambers, those kind of things. Are there enough of them? Do you have the infrastructure as far as the exhaust to add to the system if you need to, or is the control sufficient for the type of research that you're going to be doing in that space? An example would be if you need to have biosafety level 2 work, you're going to need to have negative airflow from the hallway into the lab space, and is the exhaust system able to accommodate that? Are there enough air changes in the room to keep the occupants safe? So do you have enough exhaust and volume in the air system to allow noxious fumes and things like that to be exhausted outside of the building? And finally, are the electrical loads sufficient? Do you have enough capacity in your electrical system for all of the equipment that's going to be used in the lab space? As labs become modernized, more and more technology gets used, and there are always problems with older labs not having enough outlets and wanting to run extension cords and power strips. And so when you're designing a new space, that's something that should really be looked at, is whether you have the existing electrical load, enough electrical outlets for all of the equipment that's going to be moved into the space. And as far as lab design goes, you want to make sure you're hiring architects that have lab design experience. There's a lot of architectural firms out there, design firms out there that think they can do a lab, but they don't have enough experience with the way things work after the lab's designed. Once it's been turned over to the lab workers, to ensure that things don't have to be gone back and fixed, and that's what you want to avoid, because that's just extra costs. So, verify that your architects and design firms that you're going with have designed labs in the past. And the final thing as far as lab design is make sure that you're consulting with the lab workers, managers, directors that are involved in that space. Those people on the ground have good insight, and they need to be included in the discussions about how to design the space. And they're the ones that are doing the day-to-day work and need to be included, and so because they're going to be the ones using the space after it's done. So, and then you also want to make sure the managers or supervisors are involved, because they take ownership of the programming and design of the space, and make sure they do that so they don't come back later and say, well, I never approved that. Don't let them be lazy, and make sure they're involved in the design process as well. So some of the components of good lab design are that they have designated areas for specialized research, such as microscopy, radioactive materials, pathogens, or other high hazard materials. You want to have common equipment rooms, so those devices such as freezers and other things that are shared can be in a central location and not have people going into each other's labs necessarily. Freezer farms, so-called, are rooms that are designed with augmented cooling to handle minus 80-degree freezers and other equipment that puts out a lot of heat, so they aren't damaged and you don't lose valuable research assets if they go down because they've overheated. Additionally, separate spaces for tissue culture and pathogen work should be designed so they can be separated from lower risk work, just to maintain that the people that are working with those lower risk items aren't exposed to those higher risk agents in the lab. And then also it's important to separate office and eating spaces from lab spaces. There's a lot of in the past, there's been designs where they've had desks in the lab space, and that just generally, in my experience, people tend to, if there's a desk space where they can sit down, they're going to try to eat there. And so incorporating break rooms and lunch areas into the design of a new space, which we've done with the new Vet Diagnostic Center here at Nebraska, helps eliminate that and pull those food items away from the lab spaces so you don't have that crossover. And finally, you want to make sure that the finishes are compatible with the research materials and the hazards in the labs. Generally, lab materials, as far as lab benches, are made from impervious materials that are resistant to acids and heat and other corrosive materials. And you want to make sure that the floor materials and stuff like that as well are compatible with the materials and research that's going on. So in recent years, there's been a lot of push towards moving towards an open lab design versus the traditional closed lab where each PI or researcher has their own space with a door and four walls, and they're confined to their space. There's advantages and disadvantages to both systems and design methods. The intent for the open labs really is to allow for flexibility and encourage interdisciplinary and collaborative research. The downfall with that is that it's difficult to isolate the various hazards that are present when you work in a lab with an open design. So if you say you have 4 researchers in individual labs that are pictured on the top. One works with radioactive materials, one is a chemist that does synthetic work, one is a virologist, and the last one does animal model work. If they were to move to an open concept lab like that picture on the bottom of this slide, how do you keep the different hazards that each researcher works with separated? How do you make sure that someone that works in lab A knows the hazards of what is in lab C? So there's the difficulty with the open concept, although it's beautiful and a lot of architects are pushing towards it just because it's nice open concept. A lot of people like that in their homes as well. It doesn't always lend itself to the best and safest environment for lab research. The exception to that can be incorporating those separated areas, as I mentioned before. So you can have these open concept rooms when you have labs, when you have separate subrooms that are dedicated to tissue culture or to pathogen work or radioactive material work. And that helps contain those hazards into rooms with doors that can be locked if necessary, but also keeps it out of the hazard, the main open area of the lab. And the real hazard comes into this when, like I said, you don't have knowledge of what faculty member A is doing, or the people that work for faculty member A don't know what faculty member C is working with, and there's something happens, and there's they get exposed to something that they didn't know was there. So something else to consider is making sure that those people that share those open spaces are aware of what other people are working with in that space, or you group similar researchers together in those open labs so there isn't as much of a difference between what each person is working with. So we're going to talk about engineering controls now. So OSHA defines an engineering control as a physical modification to a process or process equipment or the installation of further equipment with the goal of preventing the release of contaminants into the workplace. To the extent feasible, the work environment and the job itself should be designed to eliminate hazards or reduce exposure to hazards. So what are some engineering controls? Which of these types of controls are you currently using? Are you using a fume hood, a biosafety cabinet, a glove box? Are you using safe sharps or sharp disposal devices? Machine guarding? Do you have devices or equipment in your lab space that requires guarding, such as a lathe or a drill press or some other type of shop material if you're manufacturing in an engineering type lab? Eye washes and safety showers are also engineering controls. Are the controls current? Do they need to be updated? Are they still compliant with the standards that OSHA puts out or ANSI puts out? Are some of them unnecessary, or do you have equipment that you're not using? These are some of the things you should be asking yourself and asking amongst the design group. Is you don't want to necessarily replicate what you've already have if it's not necessary. You want to make sure that you improve upon what you've already got and take advantage of this redesign period as a chance to make those improvements. What changes do you need to make to get the best and safest lab space you can? Eye washes should be plumbed to a sanitary sewer where they're allowable. That just eliminates the chance of having water damage, because you're going to get more damage in general from the water that spills on the floor during a safety shower use or an eye wash use than the minute amount of chemical that goes down the drain. However, you do need to check with your local building codes and wastewater rules before you push for that, because there may be regulations that don't allow for those kind of devices to be plumbed to the sanitary sewer. Are the safety showers accessible? Do they meet ANSI standards, as I mentioned earlier? And make sure that you don't let people install drench hoses and call them an eye wash. A drench hose is not an eye wash. Drench hoses, an eye wash has to hit both eyes at the same time, and there are specific standards that ANSI has put out that specify how an eye wash should be installed, how a shower should be installed, and those standards should be followed when you're looking at your redesign. So as far as your procedures go, you want to ask, are your current procedures as safe as they could be? Are there better processes to achieve the same results? But you want to make sure that you don't just replicate existing processes and ways of doing things for the sake of history, just because you've always done it that way. This is a chance to look at those things and decide, is there a better way to do this than the way we've been doing it? Is there a safer way? And here are some other questions for PPE use. What PPE is needed in the lab? Is the specific infrastructure needed is there any infrastructure needed to accommodate this PPE use? An example that may not apply to a lot of you, but if you have a biosafety level 3 high containment lab, if you're using what's called the PAPR, or personal air purifying respirator device, do you have a place to store them? Do you have a place to charge the batteries in them? Those kind of things, as far as design goes, are important to consider. Do you need a shower? Do you need a shower out of the facility? At our Vet Diagnostic Center, that's something that our necropsy lab needs is shower facilities. The same with the Biosafety Level 3 lab. That's a component of that, is that we need to have that capability to shower out should it be required by procedure or containment guidelines. Are there engineering controls that can be improved to supersede current PPE use? Are you using PPE now because you don't have the necessary engineering controls to keep people safe? So those are some good questions to ask when you're looking at designing these spaces. You also don't want to, again, don't keep the status quo for the sake of convenience or historical reasons. So finally, the last component to this is the people that work in the lab. Are the staff properly trained? And again, the frontline workers should be consulted on lab design and layout. If you're not being consulted, ask to be involved in the design. Try to argue that your opinion needs to be heard, your voice needs to be heard, so you're the ones going to be working in this space after it's all done, and it needs to be a space that you're comfortable in, you feel safe in, and works to complement that with whatever engineering controls and other design elements are implemented. Some design traps that I want to highlight is to duplicate your existing design. So don't just replicate the existing design of the lab. Look at the layout. Make sure that it's the best case for you. Also, don't design for existing procedures. As I've mentioned before, you want to make sure that you're designing this for future use and for flexibility and also for the best safe procedures. Is there a better way to do this process and then involve anyone that may use the space in the design process? And that's it for me.
Thanks, Matt. All that was great information and great guidance going forward. This is Brian Garrett, and what I'm going to be looking at is using flexibility or looking at equipment selection for lab managers and safety officers once you have cataloged all of the information that Matt spoke about and that's been communicated to the design team, how flexible equipment selection can improve a building's design or maintain it for the future, all for the purpose of keeping that building, that investment going for as long as it can and maintaining efficiencies. So with that, there are numerous types of equipment that can do this. My expertise is in biological safety cabinets and hoods and ductless hoods in general. So we're going to look at it through the eyes of the biosafety cabinet, specifically Class 2, but this does spread into several other types of equipment, water systems, vacuum lines, glassware washers, pretty much any engineering control that Matt spoke of. There are ways to improve a lab design just by the selection of the equipment, and that's where you as a lab manager and the safety officers can come in to provide guidance to your design team. So the first case study I want to look at looks at how to course correct should the communication not, or I guess should there be a gap in communication between the design team and the laboratory itself. And unfortunately, we do see this quite often. In this specific case, a customer of ours called me up and said, "Hey, Brian, I've got a new design lab. Can I send you my floor space and my air conditioning or HVAC plans?" And that's what you see here. Through this mess, what I was able to identify was there were 2 Class 2 biological safety cabinets that she determined were going to be type B2 bio cabinets because they were working with hazardous chemistry and very strong odors with their biology. While looking at these plans, I also noticed that they have planned the one thing that you cannot do with a type B2 biosafety cabinet, and that is to manifold or plumb them together. I've seen for the last 8 years now, time and time again, these kinds of systems fail, and I won't go into the specific reasons. I can handle that either offline or on the question and answer session, but as soon as I saw this, I knew that they were going to have issues up front. This was the design they were moving forward with. Here's kind of a simplified version of what their lab was going to look like. They had 4 recirculating A2s back in the laboratory, and they needed 2 ducted cabinets to go next to them, again, to handle those hazards. By adopting the Class 2, the Class 2 pending definition with ANSI, with NSF, the C1, what they were able to do was maintain their chemical protection that they were requiring, but were able to use the existing designed mechanical system that manifolded them together, where the Bs would fail, and to convert to the A2s that were ducted, as you see here, they would have sacrificed the safety. So by adopting a flexible technology, they were able to get best of both worlds and avoid up to around $75,000 in change orders alone. And here, I believe, is a picture of their installation. The 2 cabinets closest to you are those Type C1s, and you can see their ductwork up above, and then the cabinet in the far corner is a 5-foot A2 biosafety cabinet. Another case where flexibility really I would say save the day, but can be used to meet other goals, was at Creighton University in Omaha, Nebraska. They commissioned a committee of eight or so people or they call their Energy Savings Committee, to look at projects that they could undergo within the university that would realize an ROI of 5 years or better for payback on energy. But their key, and what was amazing about this was even at the behest of the procurement officer and finance guys, they were leaders that said that this should not sacrifice safety in doing so. So that group started by looking at LED lighting. They replaced all of their tube fluorescents with LED. They added control valves for chilled water beams and for chilled water usage within laboratories. And then they looked at the B2 biosafety cabinets. B2s get a pretty hard rap. I wouldn't say it's a bad rap, but a hard one, because they have very high exhaust requirements. They exhaust as much, if not more, than a chemical fume hood. And they require independent, separate exhaust systems per cabinet. So what they were able to do was, again, looking at a new flexible technology, replace those aging B2s that they were going to have to replace anyway. Their current cabinets at the time had been around 15 to 20 years old. So having to purchase new equipment anyway, there was an offset in the ROI cost. But they also found that of the 12 or so biosafety cabinets that were B2s that were ducted, only 2 of them were actually being used in a way that required the ductwork. The rest of them could be recirculated back in the laboratory. So they adopted the C1 technology. Now, why did they do this? They did it because it, again, removes the need for exhaust while keeping infrastructure that they already had. But then they ran them, as you see here. You can see in the picture that they're not connected to an exhaust system. That way they were realizing an energy savings that was far superior to what they were ducting out of their building. On average, especially in the middle of the United States, energy consumption for a hood, a biosafety cabinet, any enclosure that's venting out of the laboratory and out of the building can be calculated by taking $7 or $8 per the cubic foot of minute, or CFM, per year. So a 6-foot or a 4-foot B2 running on 800 CFM is going to operate around $6,400 a year, whereas a 4-foot C1 or A2 with the canopy is going to operate about half of that. What they resulted in was an ROI of 2.6 years, so half of their minimum requirement for this project group, and an energy savings of over around $53,000 a year. That was with the 8 cabinets they replaced up front. Since then, they've added 6 more, so those numbers are almost double that at this point. So now I'm going to show a quick video to show how the Type C1 technology is able to perform and meet the requirements and do what they were looking for.
The Purifier Axiom Class II Biosafety Cabinet's 3-piece work surface looks different than any other Class II BSC. The Chem Zone, aptly named for its ability to handle microbiological applications involving chemistry, is a direct exhaust work center. Personnel protective air flowing into the cabinet and downflow air flowing over the side surfaces of the interior, colored blue, are recirculated through the cabinet's supply air system. Chemical vapors should not be introduced in these airflow areas. Air in the column above the Chem Zone, colored red, is exhausted from the cabinet in a single pass. When the Axiom is in its recirculating A mode, this exhaust air is simply returned to the lab through the exhaust interface. When in ducted B mode, chemically contaminated exhaust air is safely removed from the laboratory. A Type A BSC is not designed to handle hazardous chemistry. Type B2 BSCs can, but exhaust massive volumes of expensive room air in the process. The axiom most closely resembles the Type B1 internal airflow. However, to work safely in a B1, the operator must be trained and work behind an invisible, moving line known as the smoke split. The Axiom Type C1 is the only cabinet that reduces energy consumption while containing chemicals and is safer and easier to use because it does not use a smoke split.
So with the flexibility, the extra protection, and the lower exhaust requirements that the new technology offers, for the biosafety cabinet specifically on certain projects, there's a lot that can be done to, again, as we looked at with the first customer, the first case study, DNA Genotech, correct, if you will, the sins of the communication process between lab management, biosafety officers, and then designers. For Creighton, we looked at how this technology was able to take an existing building and infrastructure and update it to where it not only corrects the course of the building as far as its trajectory, its energy consumption and usage, but will maximize that laboratory space and fluidity from not just now but going into the future. And then finally, the last one we're going to look at is actually Matt's project, the Nebraska University Veterinary Diagnostic Center. And they did a fantastic job early on of getting the biosafety officer, Matt, his cohorts as well on the design team, the new building management system, the facilities management team, as well as the lab planning and architect, all getting together and communicating clearly what that space was going to be designed for, what they needed, and specifically what tasks each laboratory was going to be doing in selecting the equipment appropriately so that it would meet the needs of today, but also had the flexibility, modularity in some cases, to change looking into the future. So here's just a real brief section of the building's equipment schedule, and you can see on there that they're selected different sizes, but different types of hoods: Class 2 A2s, Class 2 Type Cs, fume hoods, and even laminar flow horizontal cabinets, are also known as horizontal clean benches. This is basically the shopping list that they can put together from talking with lab management. And Matt signing off, making sure that the equipment selected is what's going to work for that laboratory and maintain safety of the lab and the environment. And then they start tucking those into lab spaces. Here's just a quick key. So what we're going to be looking at are the green boxes, which are the fume hoods, blue boxes, which are recirculating biosafety cabinets, and then the red, which are the exhausted. The first lab we're going to look at, and I've selected just two of this facility where they have several floors of labs. The first one's the histology lab, where they have one fume hood off on that left wall, and then they have three exhausted biosafety cabinets. They selected and they knew those were going to be installed in an exhausted mode on the front end, so those were automatically selected as Type Cs to get that chemical protection. They also knew that if at any time those cabinets needed to be converted into a recirculating mode, they could stub off that duct and the exhaust system and save some energy on the back end as well. The next lab, which is the VS&B, or Virology, Serology, and Bacteriology laboratory, was much more complicated and a larger design because they had to work with 9 recirculating biosafety cabinets. They had 2 chemical fume hoods there on that left wall and just 1 exhausted biosafety cabinet. And they have, I believe, a couple labs that have this very similar footprint. Well, let me back up just a second. What often happens in laboratory design is that people go under, or people, but lab designers fall into a trend, or they become entrenched in the concept that without proper guidance from the facilities design crew, that they don't know what cabinets or how many cabinets need to be recirculating or exhausted. So often, instead of guessing, they'll ask the design team. The design team hasn't necessarily spoken with the lab managers and actually seen the SOPs to know what they'll be working with, so they usually just assign a number to it. So if they say, we're buying, for the sake of simplicity, 100 biosafety cabinets, I need 10% of those to be exhausted. The designer will design a lab space with 90 biosafety cabinets that are recirculating and 10 of them that are B2s, hard ducted, and can never be converted. And that lab is now, or that facility is now stuck with a very rigid infrastructure that cannot change as it goes on. A's cannot become B's, B's cannot become A's. They are what they are. The University of Nebraska took a more forward-thinking approach, and they counted up how many cabinets they needed to be exhausted up front. They knew how many they would need in total. So the biosafety cabinets that were ducted were selected to be ducted, and then a portion of the A2s, or the recirculating cabinets, were selected to be C1s as well, because they knew that if those needs changed and they needed greater exhausted capacity, that some of these blue boxes could become connected to ductwork and provide that level of protection. So from the very beginning, they knew that this building could change, and providing that flexibility is going to give them something that can grow with the university and with the Veterinary Diagnostic Center in the future. So there are 4 main points that you can get out of, and again, this applies to not just biosafety cabinets, but again, fume hoods, water systems, et cetera, that you need to look at when you're designing laboratories and when you're giving guidance to the design team for selecting equipment, whether it is what's called owner furnished, which after you take possession of your lab, you're the one buying it, or if it's going to be sourced up front by the contractor, by the lab designer. The first is lowering upfront costs, and that's done by selecting for flexibility so that the design team, the architect, the lab designer, does not over-design your facility. Second part or point is you want to avoid costly design changes during the project. And with the case of DNA Genotech, they were able, because they selected a flexible technology even after the building was designed, they were able to avoid an costly $75,000 in design change costs. There was another laboratory that's being built in New York at the Nassau County Crime Lab, where, again, designing for B2s, they wanted B2s. Their original design had all of those B2s connected to a common mechanical system or manifold. By switching to, they had the choice that they could pay that and keep their B2 design, or they could save $500,000, switch to a newer technology that's much more flexible, and then save that $500,000. Newer technology and flexible technology also often lowers lifetime operating costs because it efficiently, or it harnesses the efficiency of harmonized and modular lab design. That can be either through lowering total building exhaust requirements. In the case of water, you're not paying to purify water too early. For the case of a building water system, if you put in a high purity water system that then feeds all the labs, by the time that water gets to the point of use, it's not the same purity, and they have to repolish it or repurify it again anyway, and that becomes, again, much more costly. And then lastly, you can increase the efficiency, and that's not necessarily energy efficiency, but you increase the efficiency of the space by harnessing functionalities. You increase the efficiency of lab workers. They're not having to repeat multiple applications or they might not necessarily have to provide cleaning processes that can be automated. And then also you increase the efficiency of having of your equipment investment. You buy the right equipment up front, and if it serves multiple purposes, you're not having to put a piece of equipment into storage and then buy another piece that suits your immediate need. You're able to kill 2 birds with 1 stone. For those that did not see or had a problem streaming the video, we will be providing a link to that video and others that accompany it for various different types of equipment. So if there's any problem with that, just keep your eye out for that. And now I will turn over back to Betsy.
Thank you both. Now we'll get into the question and answer session. We do have a number of questions that have come in from the audience. For those of you who may have joined us late, you may ask questions simply by typing your query into the question box located at the bottom left-hand side of your screen. This first question is for you, Brian. Can you talk a little bit more about the hazards to biosafety cabinets that are plumbed together?
So depending on the type of cabinet that you have ducted together, specifically in the examples I used, we were looking at type B2 biosafety cabinets. Those cabinets they require an exhaust system to pull through a HEPA filter at a very high volume and high pressure. And to keep the physics short on it, there's no way to easily maintain balance between those because you're not going to work in them the same amount of time and you're not going to be working with the same hazards in them. One will load faster than the other, which throws the other one out of balance, losing your product or personnel protection and thereby risking either the process or the biosafety cabinet operator. So from that standpoint, you need to look at what equipment is being supplied and then how it should be exhausted based on national standards as well as what the manufacturer recommends.
Thank you, Brian. Dr. Anderson, can you give an example of a design trap that you've had to solve and how you did it?
I don't know that we've actually gotten caught in a trap yet. One example I can give you that happened at the university before I got here was we had a new virology building that was built around 2007, and they allowed the researchers to make a call about what type of biosafety cabinet they wanted, and they all wanted the biosafety level, the Class 2 B2 cabinet that Brian's been talking about that requires ducting. And so they got those installed in all the tissue culture rooms in the building, and when they went to commission the building, they didn't have enough air volume to balance the building's airflow. There was just too much air being exhausted and there wasn't enough air to circulate. So they had to pull all of those B2 cabinets out and replace them with A2 cabinets that had a thimble connection. So that's essentially it. They use the ducting, but there's makeup air coming from the room, and it's not all coming through the HEPA filter at that point. So that fixed the problem, but it got one of the designers, I think, got fired over it. So it was an example of what Brian was talking about, where they over-engineered the building, and it caused a lot of problems.
Thank you, Matt. This next question is for you as well. What key terms would you suggest we use when looking up building codes and sanitary sewer regulations regarding plumbing, the eye wash, or showers to the sanitary sewer?
Well, you may not necessarily. I mean, if you're, it depends on who's asking the question. If you're coming from a lab manager standpoint, I would contact your health and safety department, EHS or whatever at your institution. They should be familiar with those wastewater regulations as far as what could go down the sewer and what can't. But you can also probably contact directly the wastewater utility in your area and find out what is allowed and what isn't. A lot of times those are regulated by EPA as far as what they consider hazards, but the wastewater treatment area will generally have specifics of what they allow and what they don't allow, and it may be more restrictive than EPA or less restrictive. It just depends. well, it's not going to be less restrictive, but it may be more restrictive based on the methods that they use to treat the water in the city. So as far as terms go, I'm not sure there's anything that I can think of that would apply as far as terms, other than it'd be discharge of hazardous materials. Yeah, I would. It'd probably be easier just to contact the wastewater treatment facility directly. And at least here in Lincoln, we're in touch with them, and we consult with them to establish a sewer disposal list. So we're aware of what can go down and what can, and there isn't any extra restrictions as far as about what they don't allow to go down the sewer related to safety shower or eye wash.
Thank you. This next question is for you, Brian. Are the strategies you discussed specific to life science labs, or can they be applied to other types of lab spaces?
They are not specific to life science labs. They're not even specific to laboratories, actually. But for chemical, for labs that are handling chemistry, whether it's analytical, if you're doing trace analysis, anything like that, the ductless hoods versus filtered hoods versus ducted hoods, that question or philosophy has rapidly grown in the last 5 years, starting really in the last 25. In the last 5 years, there have been great advancements in filtration and working with an FPA, the EPA, to determine testing methods by which you can accurately select whether ductless hoods or filtered hoods can be used to replace existing ducted hoods. There are places where they can't be, but if you're able to replace even one fume hood, the typical fume hood in North America is just generally known to use as much energy as 3 households. So being able to augment or replace some of those, and again, in chemistry labs you use a lot of water systems, vacuum networks, all of those types of strategies can be used in really any lab space or even any building space to get more for your investment and really start to see some efficiencies for your laboratory.
Thank you. And that brings us to
Can I chime in on that one too?
Sure.
I just wanted to comment that as far as the ductless hoods go, you need to remember that there's more maintenance that goes into maintaining those than a fume hood sometimes too, because the filters that are used to collect the vapors do have a lifetime and they need to be replaced. So there's a little bit more peace of mind you get from having a fume hood that you know it's exhausted out of the building than there is from the ductless. So I would make sure you consult before you consider that outside of a safety officer involved in the design process. Make sure you get them involved and get their opinions. Your institution may already have a policy about ductless hoods being used in their facilities.
That's absolutely correct. 100% agree.
Thank you. We have another question. This one looks like it could be for either of you, so let's start with Brian, and then Matt, if you have anything to add, you can add to it. Outside of hoods, what is the most common problem people encounter when building new labs?
So outside of hoods and ventilated enclosures, I kind of touched on it with water. That's a system that's commonly over-designed. They'll put in high-quality polishing systems that will feed one or two stories of a laboratory building. You really want to keep any, and this is by no means a formal recommendation, but kind of a rule of thumb, that you want to keep any house-sourced water system or centralized water system to not purify the water greater than 20 to 10 microsiemen. You want to really keep it in the RO or gross deionization level, again, because by the time that purified water travels through several, it could be up to a couple 100 feet of hose or tubing. It has picked up contaminants along the way and then has to be purified again at the point of use. So typically what we see is they'll put a really high quality water system, and then they find out that they're going to cost their researchers or their laboratory budgets because they have to put in yet another purification system at point of use. If you're going to have to do that on the tail end, you may as well back off of your design or not over-engineer the design on the front end. You can say the same thing again about laboratory vacuum networks as well. Some of them forget vacuum altogether. Others have highly integrated vacuum networks, and then you put a virology or bacteriology lab in their micro lab, and they need to aspirate a maybe not even highly infectious, but a pathogenic bacteria, and they have to now source something that's, again, local and point of use. Otherwise, they risk potentially contaminating the entire building's vacuum network. And Matt can attest that one researcher does not like to be contaminated by someone else's work.
No. And do you address those vacuum networks? Sometimes there are products out there that provide point-of-use vacuum systems that are self-contained, so you don't have to risk contaminating an entire vacuum system. But especially when you're using contaminants like at a tissue culture or biosafety level 2, you want to make sure that you're using a HEPA filter before it gets to that vac line, so it traps anything before it can contaminate the vacuum line. That's not always the case with the chemical lab where you're sucking vapors, but it'd probably be good to do something similar with a charcoal filter or something else that would help block anything or catch it before it gets into the vac system. But as far as other issues, I think the biggest one, and I did mention it during my thing, is availability of electrical outlets. Because I know that's something, there's more and more little pieces of equipment that are being used to automate lab research. And if you don't have the right, electrical capability in your facility, then you're not going to be able to use those devices, or you're going to run afoul of electrical fire code violations, building code violations, as far as using, power strips and extension cords to manage all of your electrical devices. So I think that's probably the biggest one that I can think of besides the ventilation.
Thank you. We have time for just one more question, and this one is for you, Brian. Could you please describe the typical steps in a lab design process? Like, what does the laboratory or the manager need to provide to the designer?
Yeah, absolutely. So, and I'll definitely give Matt a chance to respond to this as well, since he was part of this team. The first step, and this is mostly coming actually from my lead accreditation, the first step is designing a team. So you need to put, the lab manager needs to have either everyone in their lab, or him and his the lab management assistant, or the lab manager and the biosafety officer, just a small team to kind of go over all the procedures, all the way, from daily, weekly cleaning to actual sample manipulation, sample processing, sample acceptance, and then decontamination and removal. Go through all of that and determine that what the risks are. So you go through a full risk assessment, and then they need to determine from that risk assessment what equipment, what procedures, what PPE is going to be needed to mitigate those risks. And then that information can go either from the lab manager or from the biosafety officer to the design team. And hopefully, whether it's a biosafety officer or an industrial hygienist, the safety point of contact then has a shopping list, if you will, to take to the design team, and then they can put their heads together and determine what's the best way through either the actual design of the footprint of the laboratory or equipment selection, throughput and flow of the laboratory, to get those researchers and that laboratory what it needs to mitigate that risk both to the laboratory and to the outside. So that's kind of the flow of information should start as soon as they start saying, hey, we've got budget, we're going to redesign the space, or we're going to build something new. Start with I guess, an itemization and then an assessment of risk, and then turn that into how do we mitigate that. And then that information flows through to the design team, and then that design team takes that to the lab planner and architect and says, this is what we want to build, and this is what we have to have in that building.
Thank you, Matt.
Yeah.
Did you have anything to add?
No, that sounded really good. I think it's just want to add that it's really helpful that the biosafety officer or any safety officers in general, if they have a good familiarity with the lab in the first place, that can really help facilitate that communication as well, because they already have an understanding of what kind of research is going on in the space. But again, it's good to have those discussions about what future research might be done or for future work in general, and make sure that those future desires get incorporated into design, and they consider how research might change over time. And also, the department that you're in, especially in an academic institution, will want to be involved in the design, because faculty members move around. You're not going to be there for the rest of your career necessarily, so they want to make sure that space is adaptable and can be renovated for a new occupant in the future at minimal cost. So those are some other points I would have.
Thank you. This brings us to the end of today's webinar. If you have any further questions, please consider reaching out to our presenters directly. Their contact information, as you can see, is available on the screen now. Just as a reminder, today's webinar was recorded, and you'll receive an email notifying you when the on-demand video is available. On behalf of Lab Manager, I'd like to thank Matt and Brian for joining us today, and Labconco Corporation for sponsoring this Ask the Expert webinar. This concludes today's webinar. I'd like to thank all of our attendees for taking the time out of their busy schedules to join us. For more details on all of our upcoming and on-demand webinars, please visit our website at www.labmanager.com. Thank you for joining us, and have a great day.